Are you staring at a huge list of Java number programs for your ICSE exam and just feeling completely overwhelmed? Well, what if I told you there's a secret, a kind of master key that unlocks almost all of them? In this explainer, we're going to crack that code. So stick with me, because by the end, you'll see all these different programs are really just tiny variations of one single powerful idea. Here's the plan. First, we're going to look at that dizzying list of programs that's probably stressing you out. Then, I'll reveal the one secret that solves them all. We'll see it in action, run through a quick rapid-fire round to really build your confidence, and then we'll finish up with some key tips to make sure you absolutely ace your exam. All right, let's jump right into Section 1 and face this beast head-on. We're talking about that feeling, when you open your textbook and see just how many of these number programs you're supposed to somehow know by heart. I mean, that's the big question, isn't it? Do you really have to memorize 20, 30, or maybe even more completely different programs? The sheer number of them can feel totally impossible. You've got Armstrong, Palindrome, Prime, Perfect, Spy, Niven, Automorphic. I mean, the list just goes on and on and on. It's enough to make your head spin. But what if I told you the answer to that last question is a huge, definite no? You do not need to memorize them all as separate things. You just need to get one single core concept that ties almost all of them together. Okay, enough about the problem. Let's get to the solution. In Section 2, we are going to pull back the curtain and reveal that master key I was talking about. And here it is. The secret isn't some super complex algorithm. It's a simple, really powerful loop. The core logic for pretty much all of these programs is identical. We're calling it the digit extraction engine because its one and only job is to take any number you give it and break it down digit by digit. This quote on the slide just says it all. These lines are a gift for you. You can write them with your eyes closed. This logic is so fundamental, so reliable, that it should just become automatic for you. Think of it as the foundation for everything else we're about to build.
So how does this thing actually work? It's just 4 easy steps. First, and trust me, this is so important, you make a copy of the original number. We'll talk about why in a bit. Second, you start a while loop that just keeps running as long as your number copy is greater than 0. Then inside the loop, it's a 2-step dance. Step 3, you use the modulo operator, that's the %, with 10 to just peel off the very last digit. And step 4, you use integer division, the slash, with 10 to chop that same digit off the number. The loop just does this over and over until the number hits 0.
Now for the really fun part. Let's see how this one engine can be tweaked just a little bit to solve a whole bunch of different problems.
Let's start with the most basic example, finding the sum of a number's digits. To do this, we just need to add one little thing to our engine. We'll create a variable, maybe call it sum, and set it to 0 before our loop starts. Then, inside the loop, every single time we pull out a digit, we just add it to our sum variable. Simple as that.
And this slide just perfectly illustrates the point. On the left, you've got our standard digit extraction engine. It never changes. On the right, that's what I like to call the magic line. By just sliding sum equals sum plus digit inside our loop, we've solved the program. That is literally it.
Okay, so what about reversing a number? Now that sounds way more complicated, right? But it's just a tiny clever twist. Think about it like you're building a new number. Every time you get a new digit, you have to shift the digits you already have one place to the left to make room. And how do we do that in math? We just multiply our result by 10 before we add the new digit. And would you look at that? The engine on the left is exactly the same, but our magic line is changed to rev equals rev times 10 plus digit. This simple little change completely transforms the output. You just went from adding digits up to building a totally reverse number, all with one tiny modification. That's the power of this.
All right, now for a program that really tends to intimidate students, the Armstrong number. The definition itself sounds a little complicated, right? A number that is equal to the sum of the cubes of its digits? So, for example, 153 is an Armstrong number because 1 cubed plus 5 cubed plus 3 cubed adds up to 153.
But look, the solution uses the exact same engine we've been using all along. The only change is in that magic line. Instead of just adding the digit, we're adding the cube of the digit. Sum equals sum plus digit times digit times digit. The point here is so powerful. Once you master this engine, even problems that sound really hard, like Armstrong numbers, become incredibly simple. It's always just a matter of changing that one magic line.
Okay, are you feeling confident? I hope so.
Let's kick it up a notch with a quick rapid-fire round to see how this pattern applies to even more programs. Let's go. A palindrome number? Well, you just check if the original number is equal to its reverse, and you already know how to get the reverse. A SPI number? Check if the sum of the digits equals the product of the digits. Both are easy calculations you can do inside the engine. A Niven number? Check if the original number is perfectly divisible by the sum of its digits. Now, pronic and automorphic numbers are a little different. Their main logic doesn't always need the digit extraction engine, but they still follow the same big picture idea. Do some core math, and then do a simple final check. You see the pattern, right? The engine does all the heavy lifting, and then you just do one final comparison based on what the question is asking for.
Let's move into our final section and see how this all comes together, with some super important tips that come straight from examiner comments. This is the stuff that separates the good scores from the great ones.
Okay, this is probably the single biggest mistake that students make, so listen up. Why do you need a copy? Because the digit extraction engine destroys the number it works on. By the time the loop is finished, your variable n is going to be 0. You absolutely need that original copy so you can compare it to your final result, whether that's a sum, a reverse, or something else. Don't forget this.
Here is another super common point of confusion that examiners see all the time. Reversing a number is a mathematical process. It uses modulo and division. Reversing a string is a totally different thing. That uses methods like .length and .charat. They are not the same. Don't mix them up in the exam. Finally, let's just quickly go over a few common mistakes examiners point out so you don't lose any easy marks. First, if you get a menu-driven question, put everything in one program with a switch case. Second, always initialize your accumulator variables, sum to 0, product to 1. Third, double-check your loop condition. It should be while n greater than 0. And lastly, like we just said, always compare your final result to the original untouched copy of the number, not the variable n that your loop just turned into 0. So there you have it. The big secret isn't about memorizing dozens of programs. It's about mastering one simple, elegant engine. The digit extraction engine. That's your key. So the only question left is, now that you have it, which number program are you going to solve first?